So the next talk is by Damiano Testa on metaprogramming in Lean. Great.
All right.
The stage is yours.
All right. Thank you. Thank you very much. It's great to be here. It's actually my first time in Bologna, so I'm very happy to be here. All right. So I'm going to talk about metaprogramming in Lean. And it's meant to be an introductory talk. But then I was thinking, well, everyone thinks that metaprogramming is sort of this black art where you can do whatever you want. And it's true. So I decided that instead of talking about metaprogramming, I'll show you how you can prove Fermat's last theorem. Okay, so here's the statement. Everyone can check that the statement is exactly the statement of Fermat's last theorem. And you see there's a lean proof for it. I just didn't want to bog down everything with details. So I just created a tactic for it. Less? No, okay. So I created a tactic for it, Fermat. And this tactic just proves this goal for you, okay? And after you're done with that, you can print the axioms for it, and you can check it doesn't depend on any axioms. So we're all happy with that. And if you print Fermat's last theorem, it tells you what it is. Okay. And just the docstring for the tactic was actually I used AI assistance for it. So I asked ChatGPT to write a clearly AI generated statement about this tactic. And actually, the first prompt finished with something, and then it said. So can I scroll this down? Yeah. So the second time it says, if you want it even wilder, I can do other things with it. And so I said, yeah, go for it. Okay. So, all right. So now, how does this work? Well, of course, there is something that this tactic is doing. So we're going to go and see how this tactic manages to prove Fermat's last theorem. And all of this is contained in these sort of shady Oakes lemmas file that I have here. Okay, so I'll leave you for a little bit still wondering whether I've actually proved Fermat's last theorem or I haven't, and I'm going to show you a trick. But this is kind of like one of the things that you can do with metaprogramming. All right, so let me reveal whether this is really a proof or not. Okay. So this is sort of nothing particularly interesting. First of all, we already see that there was an axiom somewhere. So there is this FLT Oakes lemma. It's sort of suspiciously called a lemma, but it's an axiom. But it didn't show up before. So let me show you that here, when I printed the axioms for this, I've been told it doesn't depend on any axiom. So this axiom that I defined there must not be doing anything. So we're not too worried about it. This is the tactic. And this is what the elab tactic, this is what the Fermat tactic does. Okay, so right now it's, well, for some of you it's very clear what it's doing. For others, it's not very clear. So let me point out that the main thing that this tactic is doing is this final line here, where it says eval tactic. So it's going to evaluate the tactic that I give it later on. And the tactic that I'm giving is exact FLT Oakes lemma. So it's actually using that lemma. And let me remind you that that lemma was actually an axiom. And it's this axiom that takes any type and gives you an element of that type. Okay, so this is just the sorry axiom, except that I called it something else. Okay. So my goal for today is basically tell you a little bit about what is going on in this elab Fermat command, and explain to you why maybe if I have time, we weren't seeing any axioms being used, even though the proof that I've constructed is just use the sorry axiom, and I've relabeled that sorry axiom with FLT-Haug's lemma, and so that should have appeared also. Okay, so because this is intended to be very elementary, please stop me if there's something that I say that you do not understand. Okay, because if you're not understanding, it just means that I haven't started early enough. Okay, so when the main thing to be thinking about when you're writing a tactic, or you're thinking about metaprogramming, or even just thinking about lean in general, is imagine that you are where the cursor is right now. Okay, so in this sort of empty space. Now, the thing that you should always remember is that it's never empty space. Okay, there's always something going on somewhere, and you're just not seeing it. Okay, so you're not paying attention, because when I'm here, lean knows that there is a Fermat tactic. Lean knows that there is that it has a docstring. It knows that there is this FLT-Haug's lemma. Okay, so there are all these sort of invisible things that exist, but you're not really seeing here. Okay? And similarly, when you're writing a proof, you're in tactic mode, and at any place where you are, you see some shadow of what lean knows, which is what you see in the info view. Okay, so writing tactics and metaprogramming in general basically is manipulating these invisible things or partly visible things and using them to your advantage. Okay, so that's what you have to do. And maybe the reason it feels like black magic is because no one is really seeing those things unless you know where to look. And so you have to learn how to look for these things. Okay, and so in order to understand this, I think so it's important to understand a little bit of what lean does when you write a tactic, and to figure out what it is that lean is actually manipulating and how you're making lean manipulate those things. Okay. So when you're writing a tactic, you're in this sort of language that's called tactic mode, where you write exact something or assumption. And the things you write there aren't really the proofs. You're writing a program that is instructing lean how to write a proof of what you're trying to prove. And so you need to be able to manipulate those things that are actually the things that lean is building as you're typing things. And if you don't want to go to that low level, you have to understand how to make lean manipulate other things that will manipulate those things below you. Okay, so, and it's always this game of I want to manipulate that thing there, but so in order to touch it, I don't want to touch it. So I take a tool that goes very far away, and then there's another tool from there that I'm operating from here, and that tool moves something else out there, and then from there something comes back here, and so you're moving something here and you're seeing its reflection there. Okay, so you should never really try to touch those things directly. You should always use these intermediate things, but we're going to see how to touch them directly, but you should never do that. Okay, so now, one of the other things that, at least for me, is always, or well, I guess it still is very difficult, is that these objects that you're manipulating, these proofs, end up being really huge. Okay, so there's, I think I even have this example here. So I checked that this lemma here is cyclotomic extension.rat.5 PID. That lemma there involves over 60,000 constants. Okay, so there's 60,000 declarations in MATLib that appear in the expression that is the proof of this declaration. Okay, and this is not 60,000 with lots of nats and nats and nats. This is 60,000 unique constants. Okay, so without repetition. So it's really, and you can imagine that then they have to be combined together. There's going to be lots of instances of the fact that you can add natural numbers, for instance. These are going to be everywhere. Okay, so it's a really immense object. And so if you're metaprogramming, you're sort of trying to construct that object. You're not going to touch each individual constant. Okay, so you have to have tools that help you do that. Okay. So the reason I'm saying this is because a lot of the times you're just copying that thing over and you're not really changing it very much, or maybe you're changing part of it, but not all of it. And so rather than moving everything around, which if you're doing math, it's okay, you sort of move the universe and nothing really happens. Here you're actually modifying something that gets written somewhere, gets recorded, gets stored somewhere else. And so one way around not having to sort of move these huge objects is to give them names. Okay, and then instead of saying, I want to move the object, you say, well, this name appears also there, and then I know that that name was associated to that representation for it. Okay, so names are much cheaper to move around because they're very short. Like this declaration is very short, it's sort of just a few characters, but it represents all of these other things behind it. Okay, so you always sort of try to work as much as possible with these representations of things that are in the things themselves. And that's sort of, again, in the spirit of, I want to touch this, but I touch something else, and that something else touches whatever I want. Okay. So from this perspective, let me explain, and then we're going to see exactly what an mvar_id is. So this is a meta variable ID. Okay. So meta variables are goals. Whenever you're in the info view and you see the thing you're trying to prove, that's a meta variable. Okay, so meta variables encode things you're trying to prove. And what you're trying to prove could be an actual proof, like I want to show that Fermat's last theorem, like what I did before, or I want to show that 2 is equal to 3. That would be a meta variable. But also, if I have something like I'm trying to prove an inequality between two things, and I apply transitivity of inequalities, then I will generate 3 different goals. One goal would be to prove that the left-hand side is less than or equal than the intermediate object. One goal would be the intermediate object is less than or equal than the final object. And another goal would be I have to provide that middle object. Okay, so these are the 3 meta variables that I generate by applying LE_trans. And so meta variables don't have to be just proofs; they can also be terms. Okay, so the object in the middle, if I'm trying to prove that 1 is less than or equal to 4, and I want to place a 1 in between, that 1 that I'm placing in between is a meta variable. Okay, in this case, if I do apply. All right, so they're very general. They are going to represent all sorts of possible things that we can ever care about in mathematics and also not in mathematics. So let's see how they're implemented. So what is an mvar_id? So I can check what it is. Well, it's a type. All right, so that's good. And if I go and look at what it is, if I figure out what is the correct combination of keys. Now, we're very disappointed. Well, okay. What it is it's a structure that only contains a name. Okay, so this is exactly what I was saying. An mvar_id represents a goal, but it's not the goal itself. Okay, so it has a name that is uniquely attached to what we're trying to prove, and there is something that will tell us how to go from that name to what we're trying to prove. But the mvar_id that we're moving around and we're passing around is only going to be a name. Okay, so that's the first level of separation from what you're trying to do and what you're actually manipulating. Okay, so let's go back to where we were. So that's what mvar_id. So, but if that's a name alone, what is keeping track of this name means the less than or equal the second thing, or the less than or equal the first thing, or the element in between? How do I go from one to the other? And that's what's called the metavar context. So let's take a look at what the metavar context is. Now you see this is much more complicated than what we had before. This is not just a name. Okay, so there's lots of things here going on. And let me point out the only thing that is relevant for what I've been saying so far is there is, if you look, I guess, usernames, but sorry, e-assignment is the thing that I care about. I guess this one here. And you see, this is a persistent hash map. So it's a function that takes the first input, an mvar_id. So that's the name of the thing you're trying to work with, and it assigns to it an expression. Okay, so that expression there is really what you would probably consider to be your goal. So when you're manipulating the mvar_id, The meta variable context is keeping track of what expression that name corresponds to. The other things do similar things for other things that you might care about. For instance, well, let me just say usernames is these goals may have names because they might have been generated by something that had a name. Like if you apply LE-trans, the assumptions there have some names that you've assigned them, so they would get that name assigned to them. So that's another function that goes now from a name to an mvarid. You see now I'm using the name that labels the assumption, and I attach it to the name of the goal that I'm trying to prove. Okay, so it's always more indirect again. And then there are other things that keep track of what is your goal state, what your assumptions are, and there is other things. Yes?
What about an expression that contains undefined method of like 3 is less than like 3 object?
Right, so that ties in well with what I'm going to say about what are expressions. So expressions can have meta variables inside them. Okay, so these are these recursive things that contain objects that refer to themselves again. Okay, so you're always touching things, and now you're sort of touching things that are touching yourself sort of far away. So it's a huge thing, and so because this ultimately is going to be an expressions, and that's what we really want to manipulate. I'm now going to probably, if I remember correctly, going to talk about expressions. No, so maybe before I do that, let me take apart the tactic that I was doing. So because I've already told you that this tactic sort of uses this sorry axiom that I've renamed, I can use it to prove whatever I want doing. So this is or sort of reading from the context that I showed you before. It's taking the whole local context, and then so these are, from the purpose of what I'm saying, these are just the variables that I have available for me. And it's looping over all of them. And so you see I'm doing this for loop, everything in the L context. And if I'm somewhere where I can see what H is a local declaration. And local declarations are basically, again, the names of the things that I have in my context. So at the place where I used Fermat, you would probably think that you have the G that I've defined to be 0. And you would probably expect nothing else. Okay, at least this is what I would guess you would expect. It turns out that because of what I've written here, this is actually wrong for 2 different reasons. There is one thing that is there that you wouldn't have guessed, or at least I wouldn't have guessed. And it's the fact that example itself is available to you, because this declaration could be recursively calling itself. So example is actually available to you. And because of a bug in what I've written, G is actually not available to you. Okay? So I'm pointing out how you can get things wrong when you're doing metaprogramming, because there's lots of traps everywhere. Okay? So, and let me show you how you can see or detect that G isn't there without doing many other things, but sort of inspecting what the code is doing right now. So this code is looping over the variables that I have in my context, and what it's doing with them, it's evaluating the tactic that's reverting the username for them. Okay, so it's doing revert the value of the tactic, the value of the variable itself. So if G were available there, this tactic would be reverting it, and then it would be proving the whole thing by applying sorry. Okay? So from the perspective of Lean, this would count as having used the variable G. Let me show you, in fact, that if at this point I revert G by hand, sorry, not H, but G. If I revert G, G is now no longer unused. Okay? So this means that my for loop missed it. Okay? Now, this is another one of these things where So so moving around these things, these meta variable contexts, is very expensive. So Lean won't do it for you unless you explicitly ask it to. And the thing is that when I wrote that tactic, that local context is not the local context at the place where I call the tactic, but it's actually the local context at the beginning of the proof. So G isn't there because I haven't defined it yet. So if I want Lean to update the meta variable context and use it at the place where I am, I have to tell Lean to do it. And that is probably the most common bug that metaprograms have. And it's the fact that before I even start this, I want Lean to use the correct meta variable context. And that's what you call with main context. Oops. And actually, maybe sort of for theatrical, how do I? Okay. So before I, oops. Okay. The context. Maybe I should have just copied it. Sorry. I'm going to erase it and rewrite it later. So let me show you what happens if I use the meta variable context. So I'm going to not move this. And so now I'm going to go here and rewrite with main context. And now you see the variable, so now it is used. Okay, so now that G was picked up by the loop, and it got reverted, and then it got absorbed in the proof because now it's proven with sorry, and so now it is used. Okay, yeah. Because it's very expensive to carry around these things. So, and
the one is that at the very beginning, right?
right. I mean, okay, maybe this is a question for someone who wrote Lean. I don't know, but I mean, I think it's because it's very expensive. I don't know.
My feeling is that general rule is start all your time with my context so that you can have it seems like
I don't know if someone from, I don't know. So I actually had a linter, surprisingly, that did that. It would just sort of take a proof and it would start the proof by saying have : equals something and then check if the tactic worked later on or didn't. And but that linter was never accepted in MATLAB. So I don't think there is any automated thing that would do it right now, but it wouldn't be hard to test. Maybe let me say, so if you write a test suite for a tactic, it's easy to automate the checking for this. But and that's what the linter that I had was doing. But all right. Any yeah.
While you're running this, I mean, right now you rely on this detection of G being unused. But I mean, are you using like printf debugging inside the which ones are used?
Oh, print what the variables are. Yeah. So I was going to do this. So and especially I want to show you what is the one that is an implementation detail. Okay, because I'm doing that there. Do I really need to do that? Well, first of all, as you can imagine, implementation details are going to cause some issue in this loop. But just so that you learn a little bit of what the thing is doing. So you see here, this line, what this line is doing, it's a value. So I wrote this with the val tactic because it means that then I write the syntax that you're familiar with. Presumably, if you're writing a metaprogram, you wouldn't really re-elaborate a lot of the syntax and you just do this at the lower level. But just for this, I think it's easier to read. So what I'm doing is reverting this variable name. And then this less than vertical bar right then means if the previous thing didn't work, then do this other thing instead. So if eval tactic failed because I'm trying to revert something that doesn't exist in the context, which would be what I would be doing if there was an implementation detail, probably, or other things, or maybe for some reason I already reverted something that sort of pulled up the variable that I'm trying to revert later on, that variable no longer exists. So then I don't want to fail because I was reverting. And so instead of doing that, I'm going to do pure unit. So I'm doing nothing basically when that previous tactic fails. Okay. So, and let me also point out that the reason I'm doing this here is because when I used Fermat on the goal of Fermat's last theorem, I had some assumptions, right? I needed the variables to be there, and I needed, I don't know, the fact that one variable was at least 3 or something like this. And so if I proved Fermat's last theorem without assuming, for instance, that n was at least 3, some of you might have suspected that there was something fishy going on, okay? So I wanted Lean to not highlight for me the fact that I wasn't using that variable. So I made it artificially used by reverting it and then proving it by sorry, okay? So that's the reason for this loop. But then once I had that loop, I could also highlight the fact that with main context, you don't pick up assumptions you create later on. All right, so after having said this, let's see what the variable names are. Oh, sorry. Yeah. So this is why you shouldn't use automated completion. So this doesn't work. And the reason it doesn't work is because it's creating a message data instead of a string. Okay, so what this is doing is tracing the current hypothesis. So it's tracing h is, and then h.username. That's the name that I would have given to that hypothesis if it has one. And its type, just because that's what I guess the autocomplete wanted me to do. And so I see this here. So you see the first hypothesis that it's looping over, it's example. And this is exactly the thing that is there because this could be a recursive definition. And we can see that this is what it is because one way of prohibiting Lean from using it is to use non-rec before the declaration. So supposedly, I really hope that if I write non-rec before example, the example here would disappear. Okay, so let me try that. It's not there. Okay, so this is always feels a little bit like magic. And this is the implementation detail, I think, that gets removed when I'm doing this. Oh, and the other hypothesis is that G, its type is not very interesting, and this is also something else that happens very much in metaprogramming. What would you say is the type of G? It's a natural number. If I go here in the proof, Lean tells me it's a natural number. Why does it say here that its type, it's unique 5333? Well, this I don't expect you to know what this is because this is an introductory thing. The thing is that when Lean creates this have, I haven't given a specification for what the type of this thing is. You see, I've written have G, that's the name, and then colon equals 0. I skipped telling Lean what the type is. Okay, Lean knows how to infer it because it sees 0. Well, I guess first it thinks, oh, 0 could be lots of things, but then it realizes, okay, but if you didn't tell me anything about 0, I'm going to just pretend that the 0 had to have been a natural number, and that's how it gets assigned a natural number. But there is a stage where Lean creates some fresh meta variables, a meta variable with nothing, and puts in the 0 in there and then tries to see what is able to fit. And so there's a process by which that free meta variable that was created, fresh meta variable that was created, gets associated to the natural numbers. Okay? And what we're seeing here is the meta variable that was created at the beginning without identifying it with what it became known to Lean later on. Okay? So this process of changing the meta variable that was created with an unknown, unspecified type to the type that it actually got assigned at some point is called instantiations of meta variables. Okay, so that's the second most common error that appears in metaprograms, is that you do not instantiate meta variables. So let's see how that would work here. So where am I printing? Oh, yes, here. So if instead of printing the type, so I've taken this local variable, h.type is its type, so that's an expression. And what I'm claiming is that this expression has an uninstantiated meta variable, but Lean knows what it is, so I can instantiate it now. And in order to do that, I'm going to start typing instantiate mvars. I hope that I have. Oh yeah, it's even telling me that there is a missing n. Okay. And so if I now look at what happens, now you see that that unique 5333 became NAT. Okay, so here. Okay. So this is what's going on. All right. Oh, I have 10 minutes left. So that's just enough time to talk about expressions. Okay, so what we've seen here, that type and the goals, these are all expressions. Okay? So expressions are what Lean uses to build proofs. So what are expressions? So I can check what an expression is. It's some type. Now here, I didn't copy what the expression is, but I just, for the purpose of showing you what the constructors of this type is. So, sorry, an expression is an inductive type. Okay, so has lots of fields. And here I'm just exhibiting the fields without copying over what the definition of expression is. But basically, I've copied it over and pasted it here, so I didn't have to switch back and forth. So here I'm listing the constructors of the expression. And notice that I leave a gap in between. So because this is an introduction to metaprogramming, and there's people that are also being introduced to Lean, let me sort of do this separation of what is an inductive type in this case. Okay, so in this case, and if I'm reading what this inductive type is doing, I can see that it has a constructor called bvar. That's a bound variable. These are the kind of things that appear in for all x. X is a bound variable because it's bound by a for all, or there exists n such that something else. The n is another bound variable. And so these are encoded by an expression, and that expression just encodes a natural number. Okay, so when there is a bound variable, you should imagine that Lean is treating that bound variable as a natural number, and that natural number is assigned by some algorithm that tells you once you enter binders, it's sort of these numbers increase or decrease or do something. Okay, so that's what the Brown index of that variable is. Okay, so it means that expressions contain all the natural numbers because .bvar7 is an expression. Then there is a similar thing for fvars. These are free variables. These are like the G that we had in the previous thing. So these are the variables that actually appear in your local context. And these are fvarids, and fvarids, just like mvarids, are just names. Okay, so they're representing some expression with some extra information, but basically it's a name that tells you, oh, it's the variable, it's the assumption that you were calling h. That's what fvarid is. Mvarid, this was the question that Michael asked. An expression also embeds all of mvarids. Okay, so an mvarid is an expression filtered through the .mvar constructor. Sorts, so .sort contains a level, that's a universe level. So those are also expressions. Const, these are probably the things that come to mind. These are sort of lemma names, for instance, or all the constants that you imagine. And so there's a name that corresponds, I don't know, for instance, Ellie trans, that's a name. And then a list of universe variable or universe levels. Those are the levels that appear in the declaration that variable corresponds to. And then there's literals. These are like strings and natural numbers. Okay, so when you write 0, Lean knows that 0 is an expression, and the expression is a natural. It's a numerical literal. And strings are also literals. Okay, so now the reason I stopped here is because up to now this inductive type is just a container for either a natural number, namely the Brown index, either an fvarid or mvarid, a level, or whatever. Okay, so far it's just a container for things that already existed before itself. All the remaining ones use the actual inductive kind of inductives. And so all the remaining constructors will actually embed an expression themselves. Okay, so this means that we're building an expression out of these main constructors that I talked about so far, plus other things that will use some combination of the previous ones in themselves recursively. Okay, so that's a common thing. Like if you've seen the definition of the natural numbers, a natural number is either 0 or the successor of a natural number. Okay, so it looks weird, but it works. And so the remaining things are application.app, and that means you take an expression, you apply to another one, like you have a function and you apply to a variable, so an element in its domain. Lam, that's a function lambda, so the lambda of lambda calculus binder. So that takes the name of the bounder. For instance, for all x, the x, so the lambda x, the x would be the binder name. And then there's the type of that x, that's the binder type. And then there's the body, which is what this thing is doing. And then the binder info is some hypotheses are implicit, strict implicit, explicit, or type class, and that's what's stored in there. And then similarly, for all e and let e and proj, these are the projectors for structures. And I skipped over metadata because I'm probably not going to say much about that. But basically, so this is how Lean encodes all of the sort of formulas that you usually see in mathematics. You can do for alls, you can do let things, you can apply things to other things. You can have the constants, so the names of lemmas and things like this. Okay, so basically, expressions are everything that you usually want to talk about. So they are the statements of your theorems and also the proofs of your theorems. And the tactic mode is a way of instructing Lean how to create an expression out of expressions that are already defined, things that are in the environment, and things that you're doing manually there. And then ultimately, Lean will take your expression that you've constructed in your proof. It will check what its type is and make sure that that type is equal to what you had set out to prove. And if that check works, you've type checked and Lean is happy and you've proved your theorem. And otherwise, there was a problem and Lean will tell you. So this is how this, yeah. So lambda is the function type. Actually, if I hover over these, I hopefully have, yeah. So it's a when you write fun x, that's the, yes. Yes. Yeah. Yeah. Anything else? Maybe just because I don't have a lot of time, just let me point out that metadata is, I think, the third most common error in metaprograms. So if you see a metadata contains some mdata thing, so that's something that is not really useful for, well, it's useful to Lean for a bunch of things, mostly having to do with optimization according to the docstring. But basically, from my perspective, a metadata just contains an expression. So it's sort of an intermediate step. You want to construct an expression, you put a metadata with something in it that I never really cared about, and then there is the actual expression you had. Okay. So a lot of time when you're doing a manual operation on expressions, you just want to filter through the M data and take an M data and use whatever you wanted to do on the expression that is contained in M data, but not on the M data itself. Okay, so that's usually called cleanup annotation or sort of all sorts of things. So it has to be laundered, and when it's not laundered, you have problems. So I'm gonna not continue anymore, but let me just point out that at this stage, when I write this have g equals 0, I've actually changed the type of the goal. This is, at least for me, it was very surprising. The have makes the goal be replaced with an M data extra information attached to the goal because I've used the have, and the term inside, the expression inside it is exactly what it was before. So at this point here, even though you don't see it, the goal is actually not what it was before. Okay, so it's something slightly different from what it was before. Okay? So that's something to be careful about. And here, if you want, I have some code that I'm not going to explain to you, just because I'm running out of time. But this is printing what the expression in the goal is. Okay, so here we have a is equal to 0, and you see this is an application of equality between a natural number and various other things. And if instead here I add have colon equals 0, you see that now the goal starts with an M data. And then it's the goal that I had before. Okay, so I've added an extra layer of things in between. But my time is up, so you can scroll through the rest of the file. These are available in the repository. And I'm going to stop here. Thank you.
Damiano?
Thank you for this talk. I think this was great. But I have one question left. You told us the first half of your Fermat tactic, the boring one that made Lean not warn about it, but how does it actually work? I mean, how come print axioms doesn't show any axioms? Would Lean fault checker accept your proof? He left us with the real questions unanswered.
Okay, yeah. So why were there no axioms left when I proved it? Well, that's because I've tricked you another way as well. So we said that with metaprogramming, you can do whatever you want. So I overrode the print axiom command. So the expression actually had that axiom in it, and Lean knew it did. But I wrote a command later down in this file, I think. Yes. I wrote a command that is called hash print axioms and then takes an identifier. It collects the axiom of that identifier, removes FLT-Augs lemma, and then does whatever print axiom would have done with the axioms that it found after I removed my lemma. So this print axiom command, if I go back to where I was, would show you, sorry, it wasn't here, it was here. So if I wrote, let me do something else. So if I could do that, but let me do something because I found it was very funny when this happened. So let me do this. So I'm going to prove true by, sorry, keyboard is not helping me. So the autocomplete has learned that Fermat is a good tactic for this, but I'm going to prove it with grind. Okay. So if I print, sorry, I got the wrong muscle memory here. So if I ask now, what are the axiom of this? You see that actually depends on prop-x, classical choice, and quad sound. So, and possibly FLT-Augs lemma, because this is my overridden thing. Okay, so that's a possibility as well, but we would never know. Okay, so the print axiom thing was sort of the last mirror that I flashed in front of your eyes. I just redefined the command to look at the axioms, remove the ones that I didn't want, and then print the other ones.
That's lovely. That's broad.
It is. No. I mean, it is fraud. But the thing is, when you're sending one of your statements to an AI agent, and you receive 20,000 lines of code, and you do these checks, have they proven something? have they flashed the mirror in front of your eyes? So anyway, you should inspect the 20,000 lines that come back to you.
So we are looking forward to, from Aristotle to find your slides and learn how to prove anything without actions. Any other questions? Yeah.
This is related to what you just said. So do you think that it's, so we saw that Lean is not very resistant against attacks, let me say. So do you think there is a way, or maybe in the future there will be a way to actually check, in the sense that we also check that the person is not pretending to have proved something, but that they didn't do something like what you did?
Right, but I mean, notice that I'm using sort of this interactive version. So if I actually use something like Lean Checker and rerun this file, then you would see, then you would run your own commands on it, and you would detect that that axiom was there. I haven't removed the axiom from the declaration. I just removed it from the printing out when I use print axiom.
So you see that if I want to be really sure, I should check with my version of print axiom that
Right.
I know what it does.
Right.
Okay.
So when I print FLT, in fact, you see that FLT AUX lemma is here.
Sure, sure.
So I haven't removed the, I mean, Lean has correctly accepted a correct proof of this statement. That statement uses a new axiom, and I'm just sort of closing your eyes when you're printing the axioms and not showing you that there was that axiom there, but the axiom is there.
So you say you didn't trick the kernel, you just tricked DAS.
Right.
Okay.
Okay, thank you, Damiano.